Hello everyone, welcome to today's machine learning virtual class with one of Google's finest, Yufeng Guo. We are excited to partner with Google Developer Group, a global community of tech change makers to deliver this virtual class. GDG is a massive and inclusive learning community in major cities across Nigeria. Just before we introduce our speaker for today, let's get to know more about Data Science Nigeria. Through our end-to-end AI ecosystem, Data Science Nigeria has a vision to raise 1 million African AI talents in 10 years. We are the #1 artificial intelligence learning community and solution delivery network in Africa. In 2019, we won the Matthal Impact Award at Doep Learning Indaba. This infographic shows our key milestones on online and offline content delivery. We have over 17,000 AI video content from top international universities curated in external drive and distributed free of charge across the country to address the challenge of poor internet. We also have over 22,000 online participants in our data science courses. We have over 271 YouTube views of the 100 days of machine learning from beginner to expert level classes. Also, we have over 3,000 hours of face-to-face free classes in data science and machine learning application in different states of Nigeria. We have over 95,000 YouTube views in 18 online classes between March and May of 2020. That's during the COVID-19 lockdown. We have over 1 million downloads of our AI for Starter free ebook. We run the biggest free AI learning platform on the continent across campuses and across cities through online, offline, project-based and content development. And here are some pictures from some of our events. We have a fast-growing community of AI Plus clubs currently in 17 universities and 23 cities. In addition, our AI Hub runs daily free classes for all categories of learners. And these are some of the pictures of sessions at the Hub. Furthermore, through our AI for Executive Masterclass, we drive industry-level knowledge and application of artificial intelligence for strategic decision making. Through the business analytics and data science trainings, we prepare and support professionals to excel in their career. At DSN, we believe that the future is now, and we must commit to building our tomorrow today. And that's why we have released the first AI book for kids. The kiddies-friendly book is available on Amazon, Apple iBook, Google Play, Jumia, and major bookstores in Nigeria. And these are just some screenshots from the book. Now, beyond our amazing impact in training and community activities, we also build AI solutions for social good. In 2019, at the Doep Learning Indaba, one of our applications, that's the Nalai application, won the second best academic research paper on fraud detection and tracking algorithm for financial inclusion. All right, today's session is part of our COVID-19 Masterclass series. But just before we introduce our speaker, let's get to watch some of the things that we at Data Science Nigeria have been doing in the last 10 weeks of national lockdown.
Raising 1 million artificial intelligence talents in 10 years cannot be stopped by a shutdown. Rather, it is a catalyst to fast-track our growth. Watch some of the key highlights on what we've been doing in the last 10 weeks of national lockdown. Data Science Nigeria, we understand that artificial intelligence or data science community building is far beyond learning meetups. It is about translating learning and research to make socioeconomic impact, create new jobs, transform ways of work, and disrupt new industries for a collective good. This is what we do so well in an inclusive, supportive, and democratic way. We are fully operating online and just a dial away. Visit our social media pages and check our past learning videos on YouTube. Data Science Nigeria is committed to raising 1 million artificial intelligence talents in 10 years.
Welcome back. Please feel free to tweet about today's class using the hashtag DSN_GDGs, and then you can mention at Yufeng G and at Data Science NIG. All right, let's get to meet our speaker for today. We are excited to have Yufeng Guo join today's session. Yufeng is a developer advocate at Google. He is passionate about how to make machine learning more understandable and usable for all. He started programming computers since elementary school. Yufeng is interested in combining IoT devices, big data, and machine learning, and loves learning new technologies. He holds a bachelor's degree in biomedical engineering with a concentration in sensors and instrumentation from Johns Hopkins University, where he graduated with departmental honors. He's the creator of the YouTube series AI Adventures at yt.de/AI Adventures. That is, you can look that link up, where he explored art, science, and tools of machine learning. In today's class, Yufeng will take us on the topic machine learning application, tools, and trends. Ladies and gentlemen, please make welcome Yufeng to class.
Hello, Data Science Nigeria. Thank you so much for joining me today. I'm really honored to be here with you all and talk a little bit about machine learning applications, tools, and trends. This presentation should hopefully be useful to both students as well as industry professionals. I'm going to try to cover not only some of the kind of tips around getting started and ways to think about problems, but also some of the emerging trends and new tools that have come out in the recent months and in the past year. So with that, let's dive right in. I'm going to switch over to the presentation here. I'm down here in this corner now, and I'll sometimes move around to other corners of the screen to try to make sure I don't cover up anything in the slides. So with that said, let's move on to, let's dive right in to kind of talking about the applications piece. But before we do that, I want to talk a little bit about this deep learning thing, right? One of the questions that came from the community was around the differences between deep learning and machine learning, which is a fair question. We hear the terms kind of used interchangeably quite a bit, and machine learning is really a bigger space around using computational approaches to try to predict or infer outcomes from data. Deep learning is a specific set of techniques targeted at typically really kind of unstructured data, pictures, audio, raw text, and it's really seen a incredible growth in its effectiveness, let's see, in the last few years. And that's mostly due to improved computation, hardware, improved algorithms, so our neural net architectures, as well as some changes to the underlying math that have improved some of the efficiencies and gains that we'll see. So we'll talk a little bit more about that in a later section. But first, as promised, applications. A lot of you asked questions about whether or not machine learning could be applied to a certain field, chemical engineering, pharmaceuticals, healthcare, and so on. And generally the answer is yes. You know, at the kind of entire industry level, yeah, you can certainly find applications to put machine learning into. The question is, what specific use cases within that industry are you trying to apply machine learning to? Because we don't want to apply machine learning to everything, just blanket it across everything. That's not the goal here, because not everything is suitable for that. If we can program something with if-else statements and for loops and the usual traditional software development and software engineering approach, that is wonderful, and we should do that, because that leads to an understandable, easily changeable set of rules that we can kind of interact with. Whereas when we build a machine learning model that's dependent on incoming data, it's dependent on the kind of slight randomness to the training process, as well as our interpretation of the outputs of that model, we are leaving things a little bit more to chance. And so we should only do that if we really need to, only if we really can't solve a problem without using machine learning or deep learning approaches. And so when we look at these applications, these industries, right, even though there's lots of different use cases to solve, there are many commonalities across them. So it may help to bring some clarity to these ideas and approaches that can work across multiple applications and industries. So let's try to think about this, these applications, not from the perspective of industries and verticals, but more around the type of data being utilized. Right? And so there's lots of other data types than what I've listed here, and many different uses, within even these data types. But this serves as a starting point. We have unstructured and structured text, unstructured and structured data. And in the unstructured realm, generally, you kind of have your pictures and video. Let me turn on a pointer here to help us indicate here. So yeah, you have your kind of pictures and video, as well as text. And so there's been a lot of advances in the unstructured side of things. And that aspect is particularly interesting in regards to deep learning. And a lot of these kind of tools and approaches carry over across different industries as long as they're using the same types of data. So let's dive into this unstructured side, right? In unstructured data, you kind of have images and text or vision and language. And specifically on the vision side, in broad strokes, there's of course much more than just this, but you could think of it as classification, saying, give me a picture, what is generally in this picture, and segmentation, which is dividing up the picture into segments. So labeling every single little pixel in this image and saying, this part is a person, this is the wall, maybe here's a painting or a picture, and so on. And then there's object detection, which is kind of putting a box around certain features of an image. Maybe you draw a box around this microphone, a box around my face. Maybe you could draw even smaller boxes around my eyes and nose and ears and so on. And on the language side, we have things around text classification. So similar to the image, given a string, marking that string as what it is. And that can actually be quite clever. You could do things like sentiment analysis. Sometimes you hear about that. That's really just text classification, right? We're putting text into these buckets of happy, sad, positive, negative, and you could even break it up further, right? You could give it a score. You could give it a score, let's say between -1 and 1, and you go by tenths. 0.9, 0.8, 0.7. Each of those could be a separate bucket. That'd be another way to label it, though typically we don't use a categorical approach for that sort of problem. Then there's machine translation, right? Using machine learning to do translation in an automated manner. That's seen a lot of improvements over the years, and we'll talk more about that today as well. And then there's language modeling, identifying the parts of a sentence or paragraph that you care about, whether it's just labeling nouns and verbs to kind of modeling the structure of language, which kind of lends itself toward the translation problem as well. And of course, there's lots of other functions, these mappings that deep learning can learn, basically, right? Everything from labeling a image with kind of a caption to transcribing raw audio into text, and we have this translation example there as well. And so let's talk about each of these in turn, right? The vision and classification sides, vision and then language. And for each of these, thinking about, I want you to keep in mind what applications you could think of in your kind of world, in your life, in your domain, in your industry. Because while the particular examples I may give aren't in your industry sometimes, right? you can generally kind of try to make that leap, make that analogy into your space, the parts that you care about for yourself, for your local community, for your business, whatever it might be. And so, looking back at history a little bit, we've kind of gone in 2011 when right before we kind of really the inflection point on improving our understanding of images, we were getting the state of the art was getting 3 out of every 4 images right and missing 1 out of every 4, which really just isn't good enough for a human interactive system, right? If every 4th thing you saw was just completely wrong, you would stop using that product very, very quickly, especially because human error is on the order of 5%. And so your expectation is that a computerized system should be at least as good as you. And so now, in just 5 short years, in 2016, that was 4 years ago, we've gone even further than that. But, you can only improve so much once you get down to just 3% error, which is quite remarkable. Let me just make sure we can still see us here. I'm going to push myself to the top right here. Now I'm up here. And, we're at 3% error, which is really quite amazing. And so I might put myself back in the bottom right here. Okay, so one of the use cases for this incredibly improved visual understanding is this case in healthcare of diabetic retinopathy, which is a kind of side effect of diabetes that causes permanent blindness. And so this is particularly acute in India, where there's a shortage of eye doctors, because you not only need an eye doctor, which is already a specialized doctor, you need a specialized eye doctor. And so they, there's this huge shortage of eye doctors, and lots of patients suffer from blindness before they can get a diagnosis. And what's interesting about this particular problem is if it is caught early enough, it's extremely treatable. Right, so it doesn't have to be a permanent blindness sentence. But the tricky thing is figuring out diabetic retinopathy, DR, is kind of tough, right? If you look at these 2 images, they're not that different. They're these little spots, and you can imagine how somebody who maybe they've been working long hours, they're tired, didn't get enough sleep last night. It's easy for a human to make mistakes, and that applies not just in healthcare, but in manufacturing, in our everyday life, right? We forgot the keys. Oh, I forgot to turn off the lights. Like all sorts of things happen. But a computer, it doesn't get tired. It might need to make sure it's plugged into the power, but other than that, it's fine. And so the Google Health team kind of applied the state-of-the-art deep learning neural networks on images to these kind of eye images. And so what they were able to do is meet the same level of accuracy as specialists in healthcare, which was an incredible result. And you can see here that this was one of the, if not the first, but one of the first kind of publications from the computer science world to show up in a major healthcare journal, right? This is the Journal of American Medical Association, not computer science. It's not IEEE or anything like that. And so this was really cool. And then later on, they actually followed it up with even better results in the following years. And so it's really quite amazing. And what was also cool as a side effect is that it was actually predicting certain markers, from these images that they weren't even looking for, so to speak. It ended up correlating to, as you can see here, things like age, gender, their blood pressure, and HbA1c, which I can't remember off the top of what it is. But it's a lot of these are blood markers, and you can kind of see how they're kind of different, right? They're showing up in the eyes because the eyes have all these small blood vessels, and so any kind of cardiovascular risk events will potentially show up earlier is the thinking there. So that was kind of an interesting direction of research and investigation that kind of the team was able to kind of pursue. In the realm of pathology, the team applied a similar kind of approach, right? They said, well, it worked with eye images. Let's take a look at these histogram slices. So these biopsy images, right? They're trying to label which areas are tumor and which areas are not. And so you can see here the basically the results are quite remarkable. And the notable values here being that the model was actually doing better than the human labeling, because I mean, these things are so detailed, right? Like you can tell they're all these little aspects. And so this then leads to the idea of building kind of a AR or augmented reality microscope, where you could have the microscope help the scientist out and say like, oh, here, this looks like it could be something bad, pay attention here, is this it? And making sure that we don't miss things, which is really quite great. And of course, in the visual realm, there's the famous examples of self-driving cars. So Waymo being one example of that, and recognizing lots of kind of the visual landscape and learning and representing that very quickly and seeing that. Another kind of fun example is in kind of the robotics realm. Google had some leftover robotic arms that were not needed anymore, and so they decided to see if they could use reinforcement learning to train it to pick stuff up. And you can see the arms kind of struggling away there, but over time it gets better at figuring out how to pick things up from their visual field, which is pretty neat. And so you can see here, this is at 5x. And the one poor researcher there sitting with a room full of robots watching it go. So lots of different ways to use machine learning, and lots of incredible advances, right? Because then here we talk a little bit about how the different kind of ways as the research has improved. In early on, the GRASP success rate was only 78%. So it's in a lot of ways similar to image classification that we saw earlier. It's like, okay, it's not really something you can rely on. And then just 2 short years later, in 2018, with a 96% GRASP success rate, I mean, that's something we can pretty much more or less rely on working most of the time, and you can just try again so you don't want it to be like a single try situation. But yeah, let's look at another example. This is again image-based for detecting diseases in the cassava plant. This was with Penn State and the International Institute of Tropical Agriculture. They were imaging leaves with cell phone pictures to find diseased plants earlier, so that they can be kind of separated from the crops. And in kind of commerce, this is a on-device model to kind of detect a similar kind of models of shoes, right? So you could be like, oh, I like this one. Let me scan it and see what kind of similar items are. So you can see it can be applied to sofas or faucets and things like that. So maybe you're visiting your friend's house or apartment, and it's like, oh, this is pretty neat. Maybe I can get one like that, and they don't remember where they got it or what model it was, and you can find something similar. So some ideas there for you. In the language realm, let's look at what kind of breakthroughs there have been on that side. So firstly, we want to think about language as this idea of sequence-to-sequence learning. So this was kind of the first step in that direction. You can think of text as a sequence, right? It's a sequence of characters, basically. And if we want to map, let's say in the case of translation, we're taking one string and mapping it to another string. So it's really just mapping one sequence to another sequence. And this principle then can be applied to things like sounds and music and so on. And so that led to all sorts of interesting outcomes, such as smart reply and autocompletes that you may be seeing pop up in both Gmail and Google Docs, as well as Google's kind of breakthrough neural machine translation system, NMT, which allowed Google Translate to not maintain kind of every language combination as a separate model, which is what they were doing, but have one basically super model that translated any of the languages to any of the other languages, which just considerably improved their just the maintenance load alone was amazing. But what's crazy is that, so you can see these translation models. These are separate statistical models, right? That's the blue bar, and this is translation quality. Higher scores, better. The neural machine translation models further improve the quality. That's the green area above each of the blue bars across the board. And it basically wiped out years of incremental improvements on each of these language models in one shot across all of these models. Just an amazing outcome. And last year, this language understanding has really gotten a lot of attention. Models like BERT and Roberta and all these BERT-based names. This one called XLNet is kind of this approach to doing one model to handle question answering, as well as sentiment analysis, document ranking, just all sorts of stuff. And so this is all moving at an incredible pace. Yeah, and so in terms of tooling, some questions people asked about TensorFlow and kind of tools to use. There's lots of deep learning libraries out there today. The two main ones are probably TensorFlow and PyTorch. They're both Python based. If you prefer a different language, there are kind of, you can access C++ kind of underlying APIs for most of these, as well as Java and JavaScript versions, at least in the case of TensorFlow. There's kind of interfaces for both of that as well. So yeah, it's particularly good for deep learning. It does cover kind of general machine learning, but usually you wouldn't use TensorFlow unless you really wanted to do deep learning specifically. It's got a really vibrant community at this point with tens of thousands of contributors, commits, downloads in the millions. So, and more importantly, I think, is the kind of community built around helping each other with regard to Stack Overflow questions, GitHub issues fixed, things like that. One of the other cool use cases I wanted to feature before we kind of moved on was this use case of keeping your cows happy. This farmer strapped put little sensors on cows, and basically they were like Fitbits, right? They were like activity monitors, and they wanted to make sure that he wanted to make sure his cows were healthy and active, because his theory was that a sad cow, a tired or sick perhaps cow, wouldn't be as active, and so that would show up in the data. And so he was collecting all this data on his cows and then trying to early detect which cows weren't doing so well. So that was another kind of cool application of machine learning. So that moves us to the next phase of our conversation, tools. This is a constantly evolving ecosystem, and though kind of industries have lots of different tools, the broad kind of tool set more or less applies sort of across the board. I'll feature some newer type things at the beginning, and then we'll talk about some more general tools across lots of use cases. So the first thing we'll talk about is the what if tool. The what if tool is focused around explainability and understanding and probing your model. The reason it's called the what if tool is kind of the idea of the fact that it answers this question of like, what if my model was this way? What if we tweaked the data this way or the inputs that way? How would that affect the outcomes? And so the tool is open source and has a number of different kind of features for doing that. I actually have a video specifically about the what if tool that dives more into it. So we won't have time to kind of go over every single tool in depth today, but a lot of these I have videos about. So I'll be sure to link to those both in the live chat right now, as well as down below in the comments. We'll add that in, or in the description below for future viewers. So this is the what if tool. It comes to us from the people in AI research team at Google, or PAIR, and it kind of can display the outcome. So this is kind of just binary classification. So you have the red and the blue, so the two categories, 0 and 1 essentially. And you can see here, this is showing that the ability to do what's called the nearest counterfactual, which is an interesting concept that I personally hadn't really been aware of until this tool came out. So just for that alone, it's pretty neat. What it does is it finds the most similar. You can select a point. Let's say I pick this red one, right? This one in the green box. It will select the data point that is most similar to it, but got categorized in the other category, right? Instead of being red, it's the blue one. What's the blue data point that's closest in values to the red one? You can see the difference between these two. Most of the categories are the same, but there are a few values that are different, and the tool has highlighted those. Another aspect of the what if tool is kind of, if you have heard of the tool called Facets, which I made a video about, this was years ago. it was a really neat tool that also came from this team. You could almost think of it as an early precursor to what eventually became the What If tool. This is Facet's overview, which allows you to see an overview of your data. You can see here there's missing, mean, standard deviation, zeros, et cetera, as well as kind of graphs of both numeric features and categorical features, which help you basically spot any kind of missing values, abnormalities, weird distributions of data, and so on. I'm also just realizing I'm covering up some of the screen. I hope I was okay in the earlier slides. So let me just drop back real quick, look at a few of these. All right, so these look okay enough. Okay, let's go forward to the next tool called Lucid. Lucid is a personal favorite of mine. I feel like it hasn't really received enough attention in the world, and so I want to kind of make people more aware of it, right? It is something that helps us visualize the insides, so to speak, of convolutional neural networks. So specifically these really large neural nets that are used in image understanding, that's what it's built for. Okay, and so it's pretty experimental, and it only supports TensorFlow 1.x right now, but it generates some really cool images around and gives you this deeper understanding of how the network is wired together. And I have a little video about this. It's actually a two-part video that leads to this concept called activation atlases as well. And I put the link here in the slides, but I'll also drop one in the live chat so that people can hopefully click it. So next up, notebooks, and more notebooks, right? Like everybody is all about notebooks. You know, ever since Jupyter Notebooks came out and then Jupyter Lab, there have been just a boom in notebook implementations across lots of different providers, essentially. Some are providing kind of a vanilla Jupyter Notebook experience. Others are more skinned, more opinionated. And so I don't want to go into each one of these in too much detail, just because for the sake of time mostly. But I'll talk about them briefly here. Right, Jupyter Lab is the original, the open source implementation that everybody kind of is aware of, I would think, I would say, and if you haven't, I would recommend you check it out. It's really kind of life-changing for people who use Python. And then everything else kind of comes from that. All right, so Colab is a free Jupyter Notebook-like environment. It's browser-based, it's free, you can get GPUs on it, but it will sometimes shut you off. There is a $10 a month Colab Pro version now that they have, which you can use and gets you better GPUs, longer runtimes, things like that. If you want something even more kind of dedicated and guaranteed, you can look at what's called AI Platform Notebooks, which is Jupyter Lab, but on your own kind of selected dedicated infrastructure on Google Cloud. And so you can kind of pick what how many CPUs you want, how much memory you want, what GPU, how many GPUs. So especially when you want more than one GPU, that kind of becomes a very appealing option. And then there's Kaggle, which is really great for its kind of data science community, similar to Data Science Nigeria. This online version, it has just lots and lots of resources in terms of data scientists doing really interesting things, and the collaborative nature of the discussions around some of these competitions are really cool. My understanding is that Data Science Nigeria has held some competitions on Kaggle in the past, so many of you I hope are familiar with that, and if you're not, definitely check that out. And also, those are also free too. They have notebooks, you can run them and add GPUs, so pretty cool. Okay, more tools. I wanted to touch on this topic around machine learning ops, ML ops, which is kind of a spin on DevOps, right? So it's like DevOps applied to machine learning. This will be more relevant to folks who are further along in their journey and are looking to potentially productionize their environments. This is probably more useful for folks who are in industry and are looking to not have to do everything manually so much. Maybe they're looking to organize their models a little more, organize their data a little more, and make this idea of pipelines like that starts becoming really appealing after you've kind of built a few things by hand. It's like, let me automate some of this stuff, right? That's what software is all about. I didn't come here to manually kick off training every single time. And so to that end, oftentimes we think about machine learning as just, do the machine learning. But in reality, there's so much more to machine learning than just the ML piece of it. And so because of that, as you begin to journey into more production-like systems that are better at scaling, have better kind of resiliency to both in terms of security, but also in terms of new data being introduced at varying rates, data that may not be super well kind of cleaned up already, right? These are real-world systems gathering real-world data. And so you end up with this long workflow of exploring your data, preparing it, feature engineering, then you maybe build a couple different models, tune them, train them, validate them, and then once you've done all that, you get to have the fun experience of deploying the models, which is basically like deploying a web server, but you had to do all that work beforehand to get there. I see I'm blocking the screen again. I'm going to pop myself up to the top right. Much better. And I think I might have blocked some of the screen here too. So I'll pop over to this slide briefly as well. So let's see. Yeah, and as a result, you kind of can think of you can take kind of your workflow and structure it into an ML ops workflow where you have your experimentation kind of zone, which then you push new code, and that updates a training pipeline, which has continuous integration and deployment built into it. And this generates what are called pipeline artifacts, which get stored in an artifact repository. Artifacts, in this case, is just referring to the code, the data, and the metadata around that, right? And that leads to training, and training, of course, has its own set of metadata, which you want to basically store in a database, tying together which version of the data, which version of the model, what parameters those models had, the evaluation outputs, and any other related kind of information that would be useful. And so then once you have that sorted, you need to determine whether or not you want to serve that model. Is the model you just created good, and is it better than what you had before? And so that leads then to a model deployment system and some sort of continuous monitoring and evaluation of that live system to ensure that it is behaving the way you think it should against real live data. So one tool that can help work with this is a open source piece of software called Kubeflow Pipelines, which is kind of this system for building these pipelines. It's specifically for machine learning, and it is built on top of Kubernetes, which some of you may have heard of. It's built for kind of managing a set of containers. And the important note here is that you don't need to kind of manage your own Kubernetes cluster to make this work. A lot of public cloud environments allow you to basically just, click and deploy a set of containers, deploy Kubernetes cluster rather, and then install Kubeflow on top of that. And Kubeflow then knows how to interact with Kubernetes, so you don't have to deal with that particular piece of it. But what you get out of it is scalable pipelines, right? And so that's the value here, is that you can have arbitrary pipeline components doing whatever you want, backed by a scalable infrastructure that allows you to spin up lots of compute resources for training, and then when it's done, automatically scale it back down. And so Kubeflow Pipeline has kind of this UI, which we saw in the previous slide. Am I still reasonably visible? Yeah, I'll move myself down. Okay. This UI that's reasonably visible and reasonably useful for kind of managing and tracking your experiments and jobs. It's specifically kind of built for that. It's got an engine for scheduling multi-step ML workflows and an SDK, very important, to kind of help you automate and define and manipulate these pipeline components. And so this is one example of a pipeline graph. You can see here that we have a couple of different steps. They're all wired together. And this is an example of how kind of complex these systems can get as you start wiring things together. And as a result, you really don't want to be managing this manually, right? You wouldn't want to run these by hand. And typically you would end up doing it by hand in the early stages, but then you would want some way to automate it. And that's where these pipeline tools come in. And so in the case of Kubeflow pipelines, basically, the pipeline is just a definition of what to run, and then you want to create a run. You want to actually do the run this pipeline, and you can run it multiple times, right? And so it's sort of like stamping out these pipeline executions, and you can even make them recurring. They don't have to be one-off. And you can, of course, view your pipeline runs, and there's really nice UIs to see and monitor your outputs, so that it's really a fairly integrated tool in that sense. A different tool that does similar stuff, and this is going to be a reoccurring theme, right, is that in the right now we're in this early days, call it early-ish days of machine learning pipelines. And so there's going to be a lot of different competing products, similar products that do the same thing, different products that do slightly different things, and you'll have to pick through that a little bit to figure out what is right for you. TFX is a more opinionated approach. It stands for TensorFlow Extended, and it's what Google uses internally. I'm going to pop myself to the top right. Oh, actually, I can go to the bottom left. Aha, I'm over here now. And it's what Google uses internally. It's in beta, and it can run on top of Kubeflow or what's called Apache Airflow, which we'll talk about shortly, which is just another kind of system that orchestrates these pipelines. And it's got all these specific components that have been finely tuned for high performance, reliability, and it kind of all operates in a certain order and a certain way. So this is what I mean when I say it's more opinionated. And so this makes it really well suited for TensorFlow-based workloads. But if you want to do more custom stuff, this may not be as suitable for you. A third version of pipeline management is called MLflow. So MLflow, you can see here, has similar types of things, right? We're tracking stuff, we have models, we want to register metadata, things like that. And so this also is a open source implementation of how you can interact with pipelines. And so I'd encourage you to, if you're in this stage of needing some kind of management tool, experiment with these, see what you like, see what you want to use, and go from there. And before we go forward, there's one more, last one, I promise, Apache Airflow. It's a bit more generic than the previous three that we saw, and it's actually designed for just all sorts of workflows. It doesn't have to be machine learning related. And so as a result, it's not quite as tailor-made for machine learning, but it does mean that it has kind of a larger audience as a result, and community size. So you might find it easier to work with in spite of it being, needing more customization due to its kind of increased community support and size. Okay, so on to the next topic. Next generation machine learning tools. I wanted to give a little preview of where I see some things developing. In particular, these new libraries coming out that all end in AX. JAX, Flax, Trax. Snacks is not real. I just thought that there's just too many models with AX. What is up with that? But hey, if you're hungry, this is a good time to maybe grab a snack. On the other hand, there really is a library called Stacks, which, yeah, we'll talk about that. It's a small neural network implementation on top of JAX. So let's talk about each of these in turn. JAX is a way to do, I guess, the core math, some of the core math pieces inside of neural networks, like auto differentiation, V mapping, P mapping, so vertical mapping, and then parallel mapping, and getting the gradient, things like that, on top of NumPy for accelerators, so your GPUs and things like that. And so it seems to be pretty well loved by the people who use it. So I'd encourage you to check it out. I did make a video about this, and it did come out already, so I'll drop a link to that in the live chat as well, so you can check that out afterwards. Flax and Trax are interesting. Flax, the F and the L, I guess, is for flexible. It's a flexible neural network implementation on top of JAX. So JAX is kind of the foundational layer for all of this, okay? And so this is what makes it next generation. It kind of is a new and different implementation of the core underlying math that's happening under the hood. And so this is it's interesting. I would encourage you to check it out. You know, especially if you've used kind of current generation tools, your TensorFlows and PyTorches and MXNets, things like that. This Flax is one way to build neural networks using JAX. JAX is like doesn't really say like you must build neural networks this way. It's just the math piece, which means you can actually use it for non-machine learning use cases as well. It's really meant to be quite broad in that sense. And then Flax is that flexible neural network implementation. And then Trax it seems unclear at first glance what it is. It is kind of more research oriented. It has a bunch of really clean implementations for kind of some state-of-the-art research models. And so from that perspective, it is really, really handy because you can get a state-of-the-art BERT model up and running relatively quickly. And so that part of it, very nice. I'm not sure what the TR in Trax stands for. I'd be open to thoughts, suggestions. And then finally, Stax is a smaller implementation, smaller than Flax, implementation of neural networks on top of JAX as well. But this one, instead of it being a separate library, is actually in jax.experimental.stax. So it's built into JAX, but it's kind of just an experimental little thing. It's a very lightweight implementation, which makes it fairly easy to read and understand. So from that perspective, it's a really nice learning tool. All right, on to trends. There's going to be some guessing ahead, and there's a little mixing of tools in here as well, kind of next generation tools. And so we'll talk about these three topics: machine learning engineering, automatic machine learning, and getting specialized machine learning hardware, and then using machine learning to design machine learning hardware. So you can kind of see where this is going, right? It's a lot about automation. So one of the things that came up a bunch in the questions before this session were around machine learning engineer, right? This title, this job role. And I've seen it come up quite a bit this year and late last year. It's really kind of coming into its own. And I think it's a way to distinguish from data science, data engineering, and research scientist, right? This role seems to be focused on the application of software engineering on the field of kind of applied ML. And it covers lots of the topics that we already went over today, especially around ML ops. And it focuses on building these production grade machine learning applications and systems, including those pipelines. And so this role ends up being a slightly different blend, right, of the typical 1/3 stats, 1/3 software development, 1/3 ML that we picture data scientists as. The stats requirement are turned down quite a bit, right? Not much in the way of stats, and most of that is replaced by software engineering knowledge and skills. And so a lot of companies really don't even require all that much in the way of machine learning experience to apply for these positions, because they are finding that the software engineering skills are so much more important to have, and you can get the machine learning stuff sort of on the job, right? Because a lot of this building is just building good quality software solutions. So that's machine learning engineering. On to automatic machine learning, automated machine learning, or in the original paper, it was called learning to learn. So in traditional kind of machine learning, and in much of state-of-the-art machine learning, we're applying ML expertise and data and throwing a lot of data at the compute, and we're making these neural networks manually. Can we use the data and the really strong computation that we have now, the hardware and the infrastructure, to make models without as much ML expertise? And so this is kind of the underlying idea behind what's called neural architecture search, NAS. And the idea here is that we kind of have this reinforcement loop that tries different architectures, trains them, sees how they do, and then tries some other architectures. And typically this will target either kind of macro scale architectures, large kind of pre-stamped out blocks and then figuring out how to arrange them, or it will be microarchitectures where it's the macro structure is already ingrained and we're just fiddling with the little pieces. So one example is kind of running through this loop of trying lots and lots of different models, and I just wanted to give you a sense of how many they're trying, right? We're talking on the order of 20,000 different models. And so far, far more than any human would want or hope to achieve. And in terms of just like you'd have to rewire it, recode it, et cetera, it would just be a pain. And so having an automated way to approach this seems to be a natural solution. And this is one of the architectures discovered by this method. These arrows are actually their interconnectivity, right? So they're just wired in all sorts of places in ways that you would never necessarily like come up with yourself. And so this was, you know, a really good model, but like you would never really come up with it yourself. So that part is really cool. And what's really impressive is that it's outperforming handcrafted models, right? So these are the top performing. So you can see here what it is it's the size of the model in kind of operations, and then its accuracy, right? And so the bigger the model, we would hope to see the better the accuracy. So let me push myself to the top right again. I keep forgetting to realign my image. Let me make sure I didn't miss something too important here. Oh yeah, I was probably blocking this a bit, but yeah. So this is what that whole slide was. And we would want to see for bigger models, improved accuracy, right? Now, of course, you're going to have diminishing returns, which is exactly what we see here. But moreover, what's cool is that the AutoML models are outperforming the handwritten models in every sense of the word, right? For the same size model, it's getting higher accuracy, and for the same accuracy, it doesn't need as big of a model. It's a smaller model, which means you can fit on smaller devices, use less computational cost, which generally leads to faster results. So really, really cool. And you can see it here in terms of same or better accuracy at a smaller size, and better accuracy at the same small size. And so this has been packaged up in Google Cloud has this AutoML thing. So they took this technology and its kind of iterations upon it and implemented AutoML across a number of domains. So we talked about images and text earlier. So that's AutoML Vision and AutoML Natural Language. They split out translation as its own thing. And for moving pictures, video intelligence is kind of what you're looking for. And they even have one for structured data as well. So for charts and logs and things like that, tables, you can use AutoML tables. There's a side tangent here. I'll go on briefly, and then we gotta forge on. Whoa, running a little bit tight on time. Is latency aware neural architecture search. So finding not just models that are high performing, but models that are fast and high performing. And so this then leads to kind of a slightly different optimization problem, and targeting getting these tasks as accurate as possible while still being fast. You can see here, I'll highlight the columns that are relevant. And maybe I'll push myself to the bottom right. Yeah, how about the bottom left? Okay. So what we have here is that for these mobile networks, we have what ended up happening was to achieve faster operations. It was basically a proxy for a smaller model. And so with fewer operations, they were getting similar accuracy at much faster latencies than the models that we had before, which is really quite remarkable. You can see these are some of the older ones, and then the MNASnet are some of the more recent ones. So you can see the accuracy is really good, but moreover, the latency is also really quite good. And the size is on the same order or smaller in many cases. And so, yeah, this is a bit tough to see the list. So this highlights it. But this bottom part is all of these models are, let me go back to the top right. there. All of these models are what this paper is talking about. And so you can compare it to all of these other ones. Now you can see that these are already, this type means whether it was generated automatically using automatic machine learning versus manually designed. And so you can see the number of multiple ads as well as the number of parameters compared to these other ones, which are of varying sizes, of course, but they're doing quite well. So with more computational power, we have an ability to kind of improve the computers that have enabled deep learning. And now that we have all this computational power and we're seeing the benefits, right? It's kind of like, okay, we have these models. We need to put a lot of compute into them to make them work. Then how can we make the hardware better, right? So how is deep learning now coming back and informing how we design computers in the first place, how we design these chips? And so this leads us to the notion of making customized hardware for deep learning, because kind of general purpose computers or CPUs, right, they have to be able to do lots of different things. But in neural networks, the operations are quite specialized. And so that leads to two extremely important properties. First, the computations are very tolerant of reduced precision. So it's fine to have a neural net do approximate multiplications like we're seeing here, rather than having all the decimals be carried through. Now, general purpose CPUs are designed to handle much higher precision operations, but that's very costly, as you can see, both for storage and compute time. And so you can pack a lot of low precision multipliers and adders onto a chip because they take up less space, and as a result perform more operations every second. And so the other piece, of course, is that there is just these handful of specific operations. We don't have to do lots of other things. And so this is what led Google back in, I want to say 2016-ish, to build the Tensor Processing Unit, TPU. This was V1. It was a PCI Express card. You can see there's not even a fan on it. It's just the heatsink. It's not terribly big, right? Like you can see the size of the screws. And that was in production use for about 4 years, and then it powered, this is actually the rack that went to South Korea. You can see the Go board there for AlphaGo, and it was where AlphaGo was implemented and everything. After that, and also I should add that this was only used for inference, only used for the predictions, not for training. So they would train it separately, then load the model onto the TPU. So from that experience, all those learnings, the TPU team then designed a V2. TPU V2 was suitable for both training and inference, and don't let this picture fool you. This is a very tall heatsink. If you looked at it from the side, it's like surprisingly high. And what it's got is each of these boards have 4 chips, right? You can see that there. And let me, yeah, I think my positioning is okay. Each of these have 4 chips. Now let's zoom in on one of those chips. This one chip has 2 separate cores, okay? And each of these cores are connected to 8 gigabytes of high bandwidth memory. That's what this little guy here is, and this one over here. And so within each core is, within each chip is 45 teraflops of power. So that's 45 trillion floating point operations per second. And let me move myself over so you can see all of that. Okay, great. And what's also interesting here is that what they utilize is what's called the brain float, which allows it to have the range of a 32-bit floating point number, but have reduced precision, basically. Fewer decimals, but it keep the same range. So that's that reduced precision idea. And so then they were able to wire them all up into what's called a pod. So they took 64 of these boards, these TPU boards, and made 11.5 petaflops. Now a petaflop is is 1,000 teraflops, right? So this is 1 million gigaflops. Yeah, something like that, or 11.5 million gigaflops. It's just insane numbers. What the layout here that you're seeing is that these 2 middle racks, the ones that are blue, are the TPU boards, and since it's just the board, we actually need to connect them to a computer, right? We need to connect them to like a host CPU, some disk, networking, memory, all that stuff. And so that's what you see on either side flanking these two middle server racks is this accompanying CPU machines. So then Google made TPU v3 with liquid cooling because, I mean, those things were getting really big, and it's blue now instead of green. And that comes, each board itself is 42 teraflops, 420 teraflops. Sorry, I think the old ones were 100 or 200 something. So that's TPU v3. And they get racked up like so. And because they're lower, the computers are actually integrated together. So there's many more TPUs per pod now, and it's got even more flops, over 100 petaflops. Earlier it was 11 and a half, right? So this is all kind of interacted through TensorFlow. You can basically use the same program with minor modifications. And what's coming down the pipeline is PyTorch integrated with XLA, which is accelerated linear algebra, will allow PyTorch to also successfully run on TPUs. So this is really enabling the next generation of machine learning kind of performance. And you can see the size of this V3 rack. It's just so many. Yeah, so you can check it all out at g.co/cloudtpu. And there's lots of reference models that you can use out of the box and then tweak, right? That's a really good way to both learn and implement real things, especially in these state-of-the-art models, is take something off the shelf, apply it to your own data set. And we'll see some more of that theme later as well. And some examples of the performance of TPU pods. So again, this is like multiple boards stacked together in one rack. So training to ResNet 50, which is a popular kind of convolutional neural net. It's 50 layers deep. On a single TPU device, on half a pod, so that's 32 of them, and then on 64. So you can see the improvements in training time drop in crazy amounts, right? 12 and a half minutes to train something from scratch, it changes the game. You don't need to wait hours and hours for something to train. You can now really run experiments without, kicking off an experiment and coming back tomorrow. You can come back after lunch. And so, yes, this is the other cool thing is because it's all combined together, it is absolutely massive batch size. It can churn through 1 million images every 8 seconds, basically. Like, it's just quite remarkable. And this is the scaling. I really don't know why I made it this way. It's unclear. It makes it look like we have perfect scaling, right? Which isn't entirely true, but it is pretty close. It's just short of like perfectly scaling. So you can see these markers of images processed per second as we add more and more TPUs on the x-axis down below here. Yeah, basically, as we add more devices, we get more performance. Usually we expect to see this kind of level off, this curve flatten, because you get diminishing returns due to networking speeds and bottlenecks and things like that. But the team worked really hard to design this system so that that wouldn't happen. You can also check out DawnBench if you haven't heard of it to take a look at some benchmarks of performance. So this is ImageNet classification, training time, and training cost. What's interesting is that even though it's expensive to run these chips on a per time basis, it trains so fast that it still ends up being cheaper than training it on slower hardware, which is kind of a crazy thing to fathom. And the reality is, of course, time is our most valuable resource. And so being able to train it faster, and in this case more cheaply, that everybody wins. So going back to our example earlier of this visual product search, this model was actually trained on a TPU by eBay, and it's like built into the eBay app now, and they basically were able to train on their entire repository of images of products, 55 million images, right? And searching through all of their product listings. And so fine-tuning that got them some really cool results. I don't know if there's a corner I can hide in here that won't block something, but yeah, this is probably as close as I'll get. Yeah, they have lots of product listings to search for sure. Okay, let's continue on. to using machine learning to design machine learning hardware. This is really exciting because using deep reinforcement learning to do chip design means that not only are we letting go and using machine learning to design our models, now we're letting go and letting machine learning design our hardware, right? And so concretely, what's happening here is we're placing pieces onto the board, designing this chip, right? So there's this idea of macros and standard cells. So the macros are the memory components, and standard cells are these logic gates. For those of you who have like an electrical engineering background or took VLSI, some of this will look kind of familiar. And the reward, what they're designing for, is reduced congestion and minimizing the half perimeter wire length, which is basically a proxy for the amount of the size of the chip and the amount of wiring that goes into it. So this is the placement of those memory components. On the left, you can see this is when they start from scratch, basically random, and then it needs to kind of figure out how to position itself, and you'll see that it will move all the macros around into this kind of circle, leaving this middle section for the kind of standard cells to minimize wire length. And then the right is a fine-tuning example where we start from where this one, the one on the left, started, and then it improves, kind of, it fine-tunes from there, and it can be a lot faster. I'll move myself over there. It can be a lot faster to kind of reach stability, right? This already is basically done, whereas this one is still kind of wandering around trying to get all its macros positioned. So really incredible advances in this aspect, right? Using machine learning to help with chip design for machine learning. And so this really leads us to the question that some folks were asking earlier: how to apply machine learning to a specific industry. And perhaps the way to answer this is to think of it in terms of the problems that are solved by guessing. A lot of what machine learning does is it takes care of some of the human aspects of problem solving for us by kind of not needing us to be there to have a human in the loop, as it were, or have the human have an easier time in the loop for these guesses. And so then combine that with what solutions are out there that you can use to address these guesses. That kind of leads you to, let me move myself again. That can lead you to some interesting kind of solutions. So where else can we use machine learning? Let me move myself again. Really need to tweak these slides so I don't block myself. One idea, right, is to think of it in terms of computer systems. Because we have so many heuristics and guesses in computing, we don't even realize it. So many of them are general kind of cases, everything from compilers to networking. There was a question about networking. All of these are values that we're kind of just guessing. You know, and it could be something that someone put a value in a long time ago, and then it just stuck. And we didn't necessarily, you know, sometimes we don't change it. We just take the defaults. A lot of times these are encoded as command line arguments, right? Like, why should we use 16, not 15, right? These things can all be tunable, and these values can all be learned through training. So how can we apply that to human systems, right? Because human systems are also, in the same way, filled with these heuristics. We make guesses and approximations all the time, right? And so at scale, especially when there's a logistical structure of kind of people passing things from one to the next and making little decisions along the way, I would think that these processes should also be learnable. But it requires that you have an intimate knowledge of your field and of your industry. And so in zooming out for a moment here, you know, machine learning kind of hardware is very much still in its infancy, and we are still kind of developing. I mean, you saw, as you can see here, the hardware is still developing rapidly. We're still applying new ways, finding new ways to solve these problems. And there are going to be significant breakthroughs ahead, both in neural architectures as well as, you know, areas that we haven't even thought of yet. So in summary, you know, with applications, we have all these, you know, we talked about these applications, but really it's about breaking it down in terms of use cases and data types. On the tools side today, we looked at this kind of constantly evolving ecosystem, and we talked about explainability, we talked about notebook tools, ML ops, as well as some of these next generation tools, JAX, FLAX, tracks, snacks, well, stacks. And finally, we looked at a little bit in terms of trends, machine learning engineering, automatic ML, specialized hardware, and then of course using ML to design hardware. And I'll draw, if I didn't already, I'll include a link to the article about that, kind of doing chip design with reinforcement learning. So one last thing is, I want to talk a little bit about how deploying ML in Africa might be different from other places, or in general, like how is deploying machine learning in your specific context different? So one is Africa has a lot of different peoples, right? And there's limited data per kind of type of user in a lot of cases. There can be situations with small data, basically. Furthermore, network infrastructure in Africa can sometimes be a little spotty as you kind of go out into more rural areas. And so that has implications in terms of on-device predictions as opposed to doing everything synchronously to a backend server. There's also the wide variety and types of devices that everyone is using, from not just Android and iOS phones, but there's flip phones and other phones too. And so and just in general, the fact that people are using phones generally more in Africa than just laptops, for instance, right? And then thinking about who is using them and where they're located and their culture, their language, and how they use them. And so that is kind of, oh, I actually had notes on those. Whoops. So we talked about data set size and variety, the connectivity between everyone. Where am I located here? I'm on the right. Okay. Maybe I'll push myself to the left. And there is the kind of the question of the devices that people are using and how that is kind of changing things, as well as the distribution of everyone all around you. And so these use cases are kind of unique in some ways. And moreover, there are specific and unique use cases that I'll leave kind of to you to think about. Right? It's your knowledge of your communities and societies that will give you a unique perspective and advantage, and which allows you to provide a tailored solution that fits in with your user base. And so this is actually true, of course, even if machine learning wasn't involved. But I would argue that because of the complexities of managing the data and model lifecycle as users interact with your application, it becomes even more important for machine learning-based applications to kind of have this all in mind, because the rules are not hard-coded and therefore therefore they're not easily understandable and changeable. And so being able to know when something is behaving strangely or wrongly, and then adjusting your application accordingly and smoothly, elegantly, that'll determine the success. That'll determine the success or failure of kind of any ML-based application or company. And so these nuances, of course, then are specific to a geography, a people, and a culture. So with that, let's move on to some of your questions that you had for me before we wrap up. So some selected kind of questions from the community here. Applications, some questions around degrees, Google research, and the future. So in terms of applications, there were some questions around applying them to all these different fields. And the short answer is yes, right? There's use cases across the board for all these things. We covered them quite a bit earlier. I'll touch on this case of limited data. You'll want to probably do some combination of data augmentation, data synthesis, and ideally maybe just gather more data, right? If you don't have enough data, try to get more data. Try to have it be privacy preserving. Make sure you're doing right by your users. But if you're able to safely get more data that will help serve your users, then try to gather more data. On the topic of degrees and portfolios, we had some questions around needing advanced degrees as well as portfolio projects. In terms of degrees, it always depends on the particulars of the company. Most that I've seen care more about experience and ability than they do about kind of degrees, but your situation may differ. Let me move myself over here. For folks who are thinking more about research, I will direct you toward a really interesting and kind of useful blog post from Chris Olah, who used to work at Google Brain and is now at OpenAI. He kind of had some thoughts about whether to do university and kind of what kind of particular use cases there were behind that. So I'll drop that link in the live chat and or down below in the description. So the next question here is around recommended portfolio projects. The short of it is, please don't build another MNIST for your portfolio. Do it for your own learning, but don't include it in your portfolio unless you have some like specific, unique perspective on it, right? It's the same reason that you would not want to include, Hello World in your software engineering portfolio. It's not particularly interesting and it's been overdone. To that end, I would also recommend not just following a tutorial that's out there and then having the result of that tutorial be a portfolio project, because the result isn't novel either. The purpose of a tutorial should be for your own learning. Now, what you can do though is apply those learnings to a portfolio project. Pick a topic that you care about, relevant to you and or your local community, right? Try to make something that's genuinely useful that will help your users or yourself do something better, faster, easier, more efficiently. The particulars aren't all that important. Nearly any real-world machine learning application, you'll encounter all sorts of amazing challenges that you'll need to solve, and it will serve as excellent material to show off as a portfolio project. So with that, let's go on to the next kind of area of questions. Folks had questions around jobs, internship opportunities in kind of the machine learning space, as well as Africa-related research topics. So first, I'll point folks to the Google AI Ghana office. We have a AI research center in Ghana, headed by Mustafa Cisse. I had a chance to meet him when just before they were launching this a few years ago. He's a great guy. I would certainly recommend checking that out if you're interested in the kind of research side of things in Africa. They're focusing on specific problems that are faced on the African continent. In terms of jobs and internships, I would recommend checking out kind of careers.google.com/either jobs or /students, depending on whether you are in industry or are a current student. There's lots of really good resources there in terms of not just job openings, but kind of career development and what, answers a lot of the questions around what certain jobs at Google look like and what they entail. So I'm going to end it here and kind of leave this all for you to think about as you kind of go on your machine learning journey. I want to thank you for joining me today, and I'll be in the live chat, answering questions as people go on. You can find out more about all the topics we talked about today. There's too many links to include, so I'll drop some more links in the live chat, and I'll give it to the organizers to share with you all. But at a high level, I have a video series called AI Adventures. You can access it here at bit.ly/AI Adventures. I've also been live streaming on a new channel on YouTube called Adventures in the Cloud over the last few months. And of course, this is the TensorFlow website, and this is the Google Cloud ML website. So with that, let me switch back to, let me put myself, in this corner here. All right. So with that, thank you so much for joining me, and, be well, be safe. And I hope that, after the pandemic is over, that in, the maybe not immediate near term, but down the road, I'll be able to come visit Nigeria and see all of you in person. But for now, I'll bid you adieu. Thanks.